So today we have two major topics to get through. The first topic is basically the last of all of our derivative applications. And the second topic, this is where we enter the dark side of calculus today. Yes, we start the anti-derivatives. You know, that's so we go from Jedi to Sith or something like that. I'm not sure. Now on the quiz, most people did a good job. A couple things that we keep forgetting, and I don't know why you would forget because it's a definition. An extrema, the word extrema means a maximum or a minimum, and it is a y value. It is not an x value, and it's not an ordered pair. Ordered pairs do not have a numerical value. The only ordered pair you will ever give as an answer in a calculus class is an inflection point because it's a point. X value is a critical number, y value is the extrema. So I'm still getting a lot of people giving me x equals 3 is the max. Well, no, that makes no sense. The y value that goes with x equal 3 might be the max. That makes more sense. The other thing is most people did a good job on the second derivative test. Either some of you didn't attend the lecture or you didn't look at the posted notes, because the second derivative test is really easy, but only about half the people even remotely attempted it. The second derivative test is you take a critical value, plug it into your second derivative, to determine if you're concave up or concave down at the critical value. So if you're concave down at a critical value, that means that critical value was at a maximum. If you're concave up at a critical value, then it must have been at a minimum. And then you simply state whatever the y value. That won't tell you whether it's absolute or local. That just goes back to the original function. And that's usually the easiest part. Now on the bonus, most of you did a great job of factoring, but some people forget, hey, what is a vertical asymptote? That's anywhere where the denominator is 0, but the numerator is not. A slant asymptote occurs when the degree of the numerator in a rational function is exactly 1 greater than the degree of the denominator, and therefore I'm asymptotic to a line. Okay, that's a nice one. And a horizontal asymptote occurs when the limit of your function as x goes to infinity or negative infinity is a constant. So if I had something like this, if I had y equals e to the negative x, okay, I'll use a simple one like this. This is never equal to 0. There's no x value where this equals 0. It never crosses the x-axis. Yet we know that if we took the limit as x goes to infinity of e to the negative x, we know that is 0. That's 1 over e to the x. What's happening is it's getting closer and closer. And so y equals 0 is the horizontal asymptote. You cannot calculate a horizontal asymptote. Mathematically, that's an impossibility because a horizontal asymptote, by definition, is what's happening to the function as x approaches infinity or negative infinity, and therefore that limit has to be a constant. It can be 0 or it can be non-zero, but it has to be a constant. If I said what's happening as I go the other way, this is rising without limit, so that would be an infinite limit. Now, this goes back to the third lecture of the semester when we looked at infinite limits. And when we did rational functions, which are our favorite, when the degree of the numerator was greater than the degree of the denominator, the limit to infinity was infinite. When the degree of the numerator was less than the degree of the denominator, the limit to infinity was 0. And when the degrees were the same, the limit was the quotient of the lead coefficients. But I have a lot of people telling me the horizontal asymptote without taking a limit because you said the function itself equal to half. I got news for you. There is no x value that exists where the function actually equals to half. The function is never equal to half. This function is never equal to 0. The horizontal asymptote is not a functional value. That actually would contradict what an asymptote is at that point. You cannot reach the horizontal asymptote. It's a limit. So a lot of folks gave me a correct answer, but you gave me a correct answer for the wrong reason. You can't get a horizontal without a limit. You can get a vertical because a vertical isn't a limit. A vertical is just, hey, I can't plug in x equal that number. I have a vertical asymptote. Those are easier to identify. But again, overall, most people did a good job. Now, the other thing is on an asymptote. If I said to you, all right, my asymptotes are 3, 5, and 7. Does anybody have a problem with that answer? Please say yes. Does anybody have a problem with that answer? The asymptotes are these 3 values.
It needs to be an
equation. You need, sorry, go ahead.
Oh, it needs to be an equation.
Very specifically, the asymptotes are what kind of animals? They are
Horizontal lines.
lines. So let's start with that. Asymptotes are lines. They're not numbers, they're lines. Oh,
So
so
it's gonna be x equals.
is it x equal 3 and maybe y equal 5? Would that make more sense then? So you never give an asymptote as a value, you give the asymptote as someone says, as an equation, very specifically of a line. But this is a vertical, this is a horizontal. If it were a slant, what would it look like? What would a slant look like?
Like an equation, like y equals mx plus b.
Beautiful, beautiful. I'm just going to write it like that. By the way, the formal term is oblique asymptote, but there's nothing in the word oblique that gives you the connotation that it's a line, and so I like slant. Slant is a slang math word, but so is max and min. You see, we don't say max, we say it's a local maximum, a local minimum. No, we say max and min. Everybody knows what that means. It's slang for mathematics, okay? But technically it's not even local. The technical mathematical term is relative. I like local because it, again, gives you the impression of what's going on. So this is how an asymptote is stated. X equal vertical, y equal horizontal, equation of a line, slant. So not just a number. So always make sure when you're indicating an asymptote that's very, very clear, and also the type. A lot of folks told me the asymptote is x equal 3 and y equal 2. Well, is one of them horizontal? Is one of them vertical? That's not implied any more than the asymptote is 3, 5, and 7. That's not implied what kind of line it is. So we just want to be a little more thorough on that. Again, most people did a really nice job. I was impressed on the bonus that so many people were able to factor it and manipulate it and stuff like that. That's kind of cool. Now, today, we're going to do one of my absolute favorite applications. And I'm going to show you where this one actually shows up. This is an application that is typically used in higher levels of mathematics and physics and chemistry and particularly statistics. And the idea is this. Keep it really simple. I have some graph. Okay, this may be a polynomial, it could be anything. Now, everybody knows whenever you're drawing a graph, the absolute easiest point on the graph to find is the y-intercept. Okay, because if my graph is y equal f of x, then this point is 0, comma f of 0. That's always the easiest point to identify in any function because I don't have to do anything. I just stick a 0 in and whatever the y value is, there's my y-intercept. We love y-intercepts, they're great. But y-intercepts aren't really that important in general because if I took this and I added a constant, I would raise the graph, I'd lower the graph, and we know we wouldn't change the shape of the graph. But if this is an application problem, it's probably, we know that things like the horizontal asymptotes, okay, or excuse me, the horizontal tangents are huge. An inflection point, maybe in there somewhere, that's really huge. But there's also something else that's really, really huge in an application problem, and that is the X-intercepts. And as a general rule, if you think about math all the way through, unless you were doing parabolas, right, the graph of a parabola, you were probably almost never asked to find the X-intercepts of your graph, because a parabola, the X-intercepts, you just have to use your quadratic formula, and that's a fairly easy thing. But in general, if I have some trig function and I ask you where it crosses the x-axis, that can be very taxing. If I gave you a polynomial of degree 3 or higher and I asked you where it crosses the x-axis, again, now I'm going to give you an absolute mathematical statement. If the x-coordinate of any of your X-intercepts is rational, then absolutely you can find it and you do not need any form of technology whatsoever. Okay, as an absolute guarantee. If it were a polynomial, it's just simply factoring. You use your rational root theorems. Finding an X-intercept when it has a rational coordinate should actually be easy in general. It's just simply solving an equation and saying, okay, x is 3 or x is 2/3 or something like that. So our goal is to find when it's not rational. What happens if this is irrational? And in fact, if I gave you a third-degree polynomial and I said, tell me where it equals 0, that means where it's crossing the x-axis, we don't actually have any techniques for that. If I can't factor that third-degree polynomial, I cannot tell you how. And computer software is not always a great idea because it can't factor it either if it's not factorable. So we have to have a better way of doing it. So I'm going to show you the technique, and the technique is called Newton's method. And by the way, I use Newton's method still to do problems right now. Even for myself, I still use this technique to do things way beyond Calc 1. Okay. I helped somebody at my daughter's school, they were doing a PhD thesis and they were using something called Planck's law in chemistry and all this, and they got stuck and they couldn't figure out how to get the answer. It was Newton's method. So I showed my daughter, and then she showed the person how to do it, and good things happened as a result. I'll tell you about that. So Newton's method, the idea, okay, I'm going to kind of blow up the curve here. So I have a curve, and regardless of what's going on with the curve, let's say, here's where the curve crosses right there. Let's make one simple assumption. Let's assume we can't find that. We don't know how to find that value exactly. Let's assume that that value is actually irrational. Okay, that makes it easy, because if that value is rational, I guarantee you I can find it in a really, really brief period of time. Even if I'm distracted, I'll find it in a matter of seconds, not minutes or hours. But let's assume it's irrational, therefore I can't actually calculate it. I gave you a 5th degree polynomial and I asked you where it crossed the axis, and it crosses at some hideous decimal. All right, so if this is irrational, then one thing is certain. There are integers on both sides of it. And let's say these are integer values. If it's irrational, it has to be between consecutive integers. That's a pretty simple idea. If that value was √2, then it's between 1 and 2. If that value were pi, then it's between 3 and 4. Okay, it's a fairly simple notion. So what we're going to do is we're trying to find that value. So before the problem starts, I have an irrational value I can't find exactly. So I want to do a decimal approximation. Now, an approximation is not the same as an estimation. Earlier, if you remember, we did the tangent lines where the tangent line left the curve. Most of you did a great job on those. And as long as the tangent line doesn't escape the curve too far, then the value on the tangent line was a very good estimator of the value on the curve. And that's where we used the squiggles, because no accuracy was implied. Okay, we did estimations. In this case here, I said, no, I have an infinite decimal sequence and I want 3 decimal places. I want 4 decimal places. I want 10 decimal places, which means all of your decimal places have to be correct. And think of the last place as being rounded. So when I enter on my calculator, √2, and then I hit equals, my calculator does this. Does that mean it terminates at 2? No, that means the last decimal place was rounded at the end to report something. So my screen has 3, 6, 9. This is a 9 decimal place approximation. This is what the definition of approximation is. It's calculated exactly correctly and rounded at that last position. If I only needed 3 decimals or 5 decimals, I would round sooner. If I needed more decimals, then I needed a more powerful calculator, right? One with a bigger display. So the idea is, before the problem starts, you already know how many decimals you're asked to calculate. So I might say, give me a 4 decimal place approximation of the X-intercept. Okay, great. That actually matters in how I do the problem. So the first thing I'm going to do is say, all right, I am going to get a starting point. Now, the starting point is really, really easy. If this is between consecutive integers, then my starting point is just going to be the halfway point. So let's suppose that that was a 3 and that was a 4. Then my starting point, I'm just going to choose 3.5. It's not a guess. It's the starting point. You chose it logically. So you'll always pick a starting point that is a very, very simple value. Generally speaking, their starting point is going to be just simply halfway between the consecutive integers. So I choose my starting point, and we call that x sub 0. Anytime you see a subscript of 0 in math or science, that always means an initial condition, a starting point. Okay, I'm choosing this. I don't calculate this. Now, with that, I want to find the equation of the tangent line. So the first thing I'm going to do is, let's say that x0 is right, let's say x0 is right there. So I want to find the equation of the tangent line that goes through x0, comma, f of x0. Now here's the nice thing. This is a rational number, therefore this will also be a rational number. Now, f of x0 is not a very good estimation. No, that's not what I want to do. I want to now calculate where does my tangent line actually cross the x-axis. Oh, so where the orange line crosses the x-axis, that's going to be my first approximation. Okay, so I picked a starting point that was reasonable. I draw the tangent line through that, and where the tangent line crosses the x-axis will be closer to the actual answer than x0 is. So I'm going to calculate where it crosses, and we're going to call where it crosses x1. Okay, now how do I find x1? Well, what's the equation of the tangent line? So the tangent line the tangent line through the point x naught comma f of x naught has slope f prime of x naught. See, this is y equal f of x. I find the derivative and I evaluate the derivative at x naught. Again, x naught is a rational number, so this will also be a rational number. So using our point slope formula, everybody remembers the point slope formula? Y minus the y coordinate, okay, y coordinate being that, equals slope times x minus the x coordinate. This is the equation of the orange line. I am interested in the y value and the x value. Well, if I'm crossing the x-axis, doesn't that mean the y value has to be 0? So the point that I'm looking for right here is the point x1 comma 0. Where it crosses the x-axis, I'm calling that x coordinate x1. So the y coordinate would be 0. So going back to here, that means this would be y minus 0 equals f prime of x naught times x1 minus x naught. I'm replacing x with x1, and I'm replacing this with the y value of 0, because that's the point on the x-axis. Okay, my goal was to find x1. So let's just work a little bit backwards here. Excuse me. So what is y? Well, y is, or I'm sorry, where are we here? F of x naught is 0. Excuse me. Swallowed a bug. Okay, so I'm going to solve for x1. I'm going to erase this. All right, so what do I actually have? Well, I have f of this y value here was f of x0. Remember, that's where it came from. I've got this backwards, I'm sorry. This should be 0 minus f of x0, sorry. That y value is 0. So when I work backwards and solve, I'm going to find that negative f of x0 over f prime of x0 equals x1 minus x naught. Okay, I'm trying to isolate the x1. That means that x1 will equal x0, I'm throwing that on the other side, minus f of x0 over f prime of x0. This calculation is actually very, very simple. Okay, so I've just identified x1. x1 is called my first iteration. What we're doing is called an iterative technique, because we're going to be doing the same calculations basically over and over and over again, seeing if we can converge to a particular value. So now I have x1. x1 is closer to the answer than x0, but it's not the answer probably not the answer. So what should I do? I'm going to do the same problem again. Now we're going to start with x1 comma f of x1. We're going to draw the tangent line through it and calculate an x2. So let's go back to this equation here. Let me erase some of this. So now I'm going to find the next tangent line. And so what I'm going to do is I'm going to now use, in my point slope formula, I'm going to use x1 and f of x1. So now my point slope formula is going to be y minus f of x1 equals f prime of x1 times x minus x1. Now that's the new tangent line that is passing through my new point. And that tangent line should pass or cross the x-axis closer to the answer than the previous one. So if I said, all right, let's call where it crosses the x-axis, how about x2 comma 0? Then going back to here, that would be 0 minus f of x1 equals f prime of x1 times x2 minus x1. And my goal is to solve for x2. So if I do the algebra, what are you going to notice here? That x2 is going to equal x1 minus f of x1 over f prime of x1. Oh my gosh, it's going to be the same form. Oh, by the way, can anybody tell me what x3 is going to be and x4 and x5 and x6? Yeah, I keep doing the process. The process technically goes forever. No, actually, it doesn't go forever. And here's why it doesn't go forever. I'm going to do the calculation on the right. I'm going to probably get an infinite decimal screen on my calculator. But remember, I said we want a particular number of decimal places. We wanted a 3 decimal place answer or a 4 decimal place answer or whatever. So what we do is we actually round off the calculation for x1. We round off the calculation for x2 and so on to the preset number of decimals. At some point really, really soon in the process, when you round off your calculation, you're going to get the same value twice in a row. And once you get the same value twice in a row, that means you're going to get that value forevermore, meaning that's your answer. And most of the time, you're going to get that value by the time you get to x2 or x3. It's actually ridiculously fast how simple this is and how quickly your answers converge. So we're going to do several examples so you can see. So now the final piece of the puzzle is, if I keep doing this process, I don't want to write down this formula over and over again. So the way we write the formula is this. The n plus first iteration is equal to the nth iteration, right? One less, minus f of the nth iteration over f prime of the nth iteration. And this is the magic formula that applies to all Newton's method problems, okay? This is the formula I'm going to use every time I use Newton's method. So the only thing I have to have an f of x. I'm going to have to take a derivative at some point, and I have to choose a starting point. That's the x naught. Everything else is just automatic at that point, and we just go through the process. It's pretty clean. You're going to like this. So let's do a problem from beginning to end. We're actually going to do several. So what I just did was the development to come up with the formula. Now we're just going to use the formula. So consider, let's say f of x is, let's start with something really simple. F of x is 2x cubed minus, how about 3x? I'll come up with something relatively simple. All right. Minus 7. Okay. And I want you to find now, when I'm finding an x-intercept, I'm finding an x value that causes the function to equal 0. We have two names for that typically in algebra. We call it the root of the polynomial or the 0 of the polynomial. And both of those terms can be kind of confusing. Whenever you say the root of something, you're not talking about square root. You're talking about a value that makes the function 0. I'm trying to find the x value that makes f of x equal to 0. That's called the root of the polynomial or the 0 of the polynomial. And both of those terms are kind of confusing. So I want to find the root. Okay, how about between 2 and 3? I believe that will work. So what we're going to do is off to the side. Now there's two ways I can ask this question. I can just say find the first positive root, in which case you got to do a little trial and error because you need to know where it crosses the axis. See, right now if I say f of 0, that's -7. What's f of 1? 2 minus 3 minus 7, that's -8. What's f of 2? That'd be 16 minus 6 is 10, minus 7 is 3. Actually, this should be between 1 and, sorry. I didn't do a very good job, between 1 and 2. Sorry about that. Okay, so I cross here, obviously, because it's a polynomial. I went from negative to positive, so I'm going to cross between 1 and 2. All right. So I'm going to find the root of this polynomial between 1 and 2. That's it. That's all I got to do. Now, I don't know where it crosses. I just know it's going to cross between 1 and 2. Will it cross closer to 1 than the other? Maybe. Is that important? No. A lot of people will say, well, you know, clearly it crosses way closer to 2 because this is closer to 0 than that. That would be true if it's a line. This isn't the line, it's a cubic. You don't know where it crosses. It might cross way closer to 1. It might cross. No, so we don't do either one. We just say, no, we're going to pick our starting point to be halfway between. So we're going to choose our starting point to be 1.5. That's it. The only possible starting points you can have, by the way, are 1, 2, or 1.5. You're generally always going to pick the one that's halfway in between. That way you don't have to think about it. You just do it. Now, having done that, I need a derivative. Okay, so what is f prime of x? That's going to be 6x squared minus 3. All right, so I need to do the following thing here. Now, my n plus first iteration is my nth iteration minus the function. And by the way, those subscripts are actually important. They might seem tedious, but they are important because xn and xn plus 1 aren't the same values. So when I insert x0 into this, I'm going to come up with x1. Then I'm going to stick x1 into this and come up with x2 and so on. Now, if you look at that, that looks very big and scary and kind of taxing and nasty. So I have a simple trick that I always do. Okay, I always simplify this as one quotient. Turns out you will reduce the amount of algebra significantly. And here's what I mean. Let's just do some scratch work off to the side. If I have the following, if I said put this over a common denominator, what would you get? Oh, okay. If I say put it all over a common denominator, then I'd multiply top and bottom, right, by 6x squared minus 3. So that'd be 6x cubed minus 3x. And now I'm going to subtract that whole quantity. Okay, I think we all agree this is what it would look like if I put it over a common denominator. Now when I distribute on top, I'm going to get 4x cubed. These will cancel. I'll get plus 7. Oh, so this problem right here where I have exactly 4 different places where I have to insert my x value. I don't care how good your calculator is. That's a lot of parentheses and a lot of, stuff. This reduces to this. This is a lot simpler. I'd rather insert my numbers into here. Now, always be very careful if you're going to do this, that you distribute correctly and that sort of thing. So this is actually equal to 4x cubed plus 7 over 6x squared minus 3. Okay, so this is the formula I'm going to use in this problem. Okay, now we should be done in about a minute. Let me erase this. So now, let's suppose, by the way, I did not say how many decimals. Sorry, I should have said that. Find the root between 1 and 2. Let's say, let's keep it simple, to 3 decimals. Okay, let's find the root to 3 decimals. Now I'm going to write x0 is equal to 1.5. That's not rounded off. That's an exact terminating decimal. Now we're going to calculate x1. Okay, so take 1.5, put it in there. So 4 times cubed plus 7 over 6 times okay, so I got some big, icky, nasty decimal on my screen. Okay, my suggestion is always do it twice, by the way, in case you made a misentry. So what do I write down? I have 1.95238, blah, 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 blah. Well, I said 3 decimal place accuracy, so I actually write this down to 3 places. Now, is this an equals? No, the equals is an infinite decimal sequence. This is an approximation. That's what the dot reverse. Oh, this is exactly 1.5. This is not exactly 1.952. This is an approximation. I've rounded it to 3 decimal places. Let me just double check my calculations. I always do everything twice if I can. Okay, now, what is x2? X2 is I take this value exactly, not the infinite decimal screen. No, 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 no. I take exactly this value. This is the only area in mathematics where you intentionally reinsert a rounded off number. Now, most of you know whenever you're doing calculations, I don't care if you're in a physics or chemistry class, and you did a calculation, you always put the whole thing. You know, if it's a root, if it's a pi, you put the whole thing in. You only round off the answers. You don't use the rounded off stuff to do your next calculation, unless you're doing an iterative technique, because what you're trying to do is get the numbers to converge to the same 3 decimal place number. So if I use the entire decimal screen, I'm never going to get the final answer. It's going to take me forever. So let's take that number, insert it into here. Okay, now my screen says something big and hideous and evil. So I'm going to take the first 3. So it's 1.850 is 3 decimal places. And yes, do write down the 0 because you're indicating that that's the 3 decimal places. Now, when I do the next calculation, I'm going to use exactly that. And my calculator now says 1.8435, which would be 1.844 if I round it to 3. Now, notice what's happening. Big jump, much smaller jump, teeny tiny jump. I suspect we may have hit our mark. I do not know what the answer is. I do not have the same value twice in a row. I have to have the same value twice in a row for me to be done. I suspect, because this changed so little, that we might be there, but until I put the number in, I won't know. And my calculator gives me the exact, almost identical screen. Okay, so now I write x4, and I got the same thing to 3 places. What this means is x5 will be that number, x6 will be that number, x7 will be that number. That means I must be done because I got the same value to 3 decimals. Remember, my final answer is irrational. My final answer is not a rational number, it's irrational. But I'm saying to 3 decimal places, this is the final answer. It's an infinite decimal, but if I'm correctly calculating and rounding it to 3, then that's the answer. So now I will report the answer. The answer is x is approximately 1.844. This is the answer. These are my calculations. I haven't answered the question. This is all the work required to answer the question. This is the answer. Now, I'm pretty sure I did this correctly. I'm pretty sure. You've seen the whole series of commercials where they do pretty sure. They stole that from me. I've been doing pretty sure for years and years. I'm pretty sure this is correct. Can I be more than pretty sure that that answer is my X-intercept, or is to 3 decimal places my X-intercept? Can I be more than pretty sure? Anybody want? How can I be more certain?
So technically, because we are finding 0, we can.
I lost your sound. Anybody want to finish the sentence?
Plug it into the equation, see if it comes to 0.
Put this into here. By the way, since this is a rounded off value, even if this is absolutely correct, but it's rounded off, if I put it in there, will I get exactly 0 back again? No, if my answer was supposed to be, let's just say square root of 2, and I round it to 3 places and I plug it in, it's not going to give me exactly 0, but what should be is very close to 0. I'm using a 3 decimal place rounded off value. So let's just find what it is. By the way, this is a check. This is the answer. I'm done. But you always do the check. So now let me do f of 1.844. I'm going to do that on my calculator because I can. So 2 times 1.844 cubed minus 3 times 1.844 minus 7. So when I do that on my calculator, my calculator says it's approximately 0.0084. That's not equal to 0, but it's pretty darn small. I have another way I could, if I went up or down 1 digit from the 4, this value would be a little further from 0. There is no 3 decimal place number that exists that will get me closer to 0. The fact that that's so close to 0 tells me, I'm pretty comfortable with that answer. What if I put that in there and I got, 52.5? That's probably not a good answer. Now, are there things that can go wrong? Well, you're using a calculator. You just got to make sure you're hitting the buttons correctly. This is why I say generally, always do every calculation twice. I taught statistics for many, many, many years. And anybody who's had statistics, the math and statistics is usually add a bunch of numbers, maybe divide that sum by a single value, and occasionally you're going to take a square root. I mean, that's the highest level of math you do in stats. People talk about stats being a hard math class. I laugh. I think any human being could pass stats after about 3rd or 4th grade because there's no math whatsoever in statistics. You're adding, you're multiplying, and occasionally taking a square root. That's it. You're not doing anything else. Yet people will say, well, I have this super powerful calculator. I used a computer and I still got the wrong answer. Yes, because you had to enter the values. If you make an entry error, it doesn't matter how good your software is. I answered a different question. So always do the calculations a second time just to make sure you didn't hit the wrong buttons. And when we first did the simplification to get this, sometimes we mess up. Sometimes our algebra goes astray and we can actually have a wrong value. So always check yourself as you go. Now, this is kind of the standard that most people think of when they think of Newton's method. I'm going to find where the polynomial crosses the x-axis. That's boring. Any cheap graphing calculator can do that for you. Now, you want something, you want to be able to do stuff a little more powerful than this. So we're going to do some little higher level problems now. All right. Now, if we go back a little ways, all right, maybe when your parents were in college, all right, if your parents went to college and they went to Mesa College and they had Mr. Brown for math, they had calculators. But you know what? The first calculators came out in the late 70s. They added, subtracted, multiplied, and divided and had no order of operations. So you actually got the wrong answer if you had multiple operations most of the time. It took a little while. They finally, they kept upgrading. Then the first graphing calculators came out in the early 80s and they were really bad because the majority of all graphs were incorrect. There was never a graph to the left of the y-axis because they couldn't handle negative input. And if you were doing roots, at least half of all roots will give you the wrong answer. It would say error. Even if you said the cube root of a negative number, it would say error. Okay, they were not good. It took a long time. But something like this is a cheap, this is like a $9 calculator, has 200 functions. This calculator didn't exist in the 90s. And anything that did what this did, you were going to spend over $1,000 on. This is $9. What I mean is there weren't even square root keys for the first 10, 15 years of calculators. There weren't log keys, there weren't trig keys on a calculator that was affordable for a really long time. So here's the thing. I needed to do a calculation and, I got one of those old cheap, I just met with my financial planner, my retirement guy last week. And it was funny. He was going over some numbers and he had one of those calculators that added, subtracted, multiplied, and divided and nothing else. So, and he's doing all this number crunching. I'm just laughing. Oh my God, how inefficient. Like, you can afford a real calculator. He goes, I'm comfortable with this one. But what if you had to take a square root? What if you had to do something more complicated? So here's what I want to do. I want to approximate the square root of 90, how about to 2 decimals? All right, I want to approximate the square root of 90. So I just use my calculator. We're going to get in a time machine and go back a generation where it didn't exist. Or better yet, You don't have, you have a cheap calculator in front of you. You have a calculator that adds, subtracts, multiplies, and divides, but doesn't have a square root key, meaning you don't have the technology to physically do that. Can you still do that? Yeah, we're going to use Newton's method to do this. And it's actually a very, very simple process. So Newton's method, I have to have a function though. I don't have a function. Well, let's make a function then. So let's let x equal the square root of 90. Well, if that's true, doesn't that mean that x squared equals 90? And if that's true, doesn't that mean that x squared minus 90 equals 0? The point of Newton's method is to figure out where your function equals 0. That's it. That's all Newton's method is for. So I think we figured out what we're going to call our function. We're going to call it that. So f of x is going to equal x squared minus 90. And I think we all agree that the square root of 90 will satisfy this equation. Oh, okay. So when I figure out, by the way, I already know the answer to this equation, where this is 0 is square root of 90, but now I have something I can take a derivative of, which means I can now use Newton's method to do that approximation. So f prime of x is 2x. So if we did x minus f of x over f prime of x, and let's put this over one denominator. I'm doing my scratch work. So that'd be 2x squared minus x squared minus 90 over 2x. And that would be x squared plus 90 over 2x. Great. That's my scratch work. Now I can say the n plus first iteration, which is the nth iteration minus all this. I'm going to use this. You don't have to do what I just did, but it's always easier if I do this, right? It's easier than using this quantity. Now we need a starting point. What should my starting point be? Well, square root of 90. I don't think that's going to be that hard. You see, what's f of 9? That'd be 81 minus 90. That's negative 9. What's f of 10? That'd be 100 minus 90, which is 10. So why don't we choose our starting point to be, how about, I don't know, 9.5. Now think common sense. Square root of 90, shouldn't that be somewhere between square root of 81 and square root of 100? That's what we just did. I don't know what square root of 90 is, but I'm going to use 9.5 as my starting point, because after I chose my function, right, consecutive integers 9 and 10, I changed sign between them. And I made the square root problem into a rational function. I made it into a polynomial kind of thing. Automatically, that makes my life a little bit easier. Let me grab it. All right, so now let's find x1. And that's going to be an approximation. So I'm going to take the 9.5 and put it right into there. So if my x0, and by the way, don't do this. Don't do this. All right, 9.5, and I'm going to square it and add 90, and then do 2 times 9.5, and then I'm going to calculate that and then add it to 90. Then I'm going to calculate that, and I'm going to keep rewriting all those calculations until I'm done calculating. I assume that all human beings are going to put this into here using their calculator. I really don't need you to tell me what 9.5 squared is, and then what that plus 90 is, and then what that divided by 19 is. No, just never write this down. Just do it. That's why you wrote this, so that you have some place to insert it. Having said that, people will still do all of this extra work and make mistakes because they're doing all sorts of extra work. I don't want you to make mistakes. All right, my first iteration, I said to 2 places. I got 9.486 something, so to 2 places, that would be 9.49. Now let's do our second calculation. That means I'm going to use 9.49. Remember, I said 2 places this time. So put 9.49 in there. And I got, oh, same answer. Gee, what do you know? I'm done. We started with our initial, I don't like to call it a guess. It's our starting point. Our first iteration, we got the answer. We got it on the very first step of the problem. But I don't know that I got the answer until I did it a second time. So you gotta be really careful. Never stop until you have consecutive iterations be the exact same value. Now, if I go forever more, I'll still get the same value. So right now, my final answer is, remember I said, approximate this. So the final answer is this. Root 90 is approximately 9.49. That is my final answer. And if I use my calculator to check, I don't need to check the function. Now I can just go square root 90. And I got that. Okay, 9.49 to two places. Beautiful. And you're wondering, okay, I could actually do any root. Now, here's the funny thing. People say, well, I have a square root key on my calculator. Yeah, but what about a fourth root key or a fifth root key or a sixth root key? Believe it or not, those calculators didn't exist for a long time. Square root keys were added, but then it was another 10 years or so before other roots were added. It's really kind of funny that there are certain things that didn't get added till way later into the calculators, but I can still do this problem. Yes, having a calculator with a square root key is far more efficient. All right, let's do one more of this nature. All right. Let's consider the graphs of y equals cos x, and how about y equals x? I want to consider these two graphs. Well, let's start with y equals x. That's easy. Now, what does the cosine graph look like? Cosine graph, we know, kind of goes, okay, it goes forever and ever and ever. You know, but there is something interesting about these graphs. They actually do intersect at exactly one place. Can anybody tell me where they intersect, by the way? I'm just curious. Where exactly does the cosine graph and y equals x intersect? Anybody know the answer off the top of their head? No, neither do I. It's some hideous irrational value. So let's find it. I want to find that point right there. And I think we can probably use Newton's method. Oh, what do you think? I can use Newton's method to find that value. Well, how am I going to find that value? What do I take the derivative of? Oh, we have to create a function first. I need to know, therefore, really, you need to solve cos x equals x. Isn't that exactly what we need to do? To find that ordered pair, I need to figure out where these guys intersect. Oh, so why don't I write it as maybe x minus cos x equals 0? By the way, it doesn't matter what order I subtract. Then I will make my function. I'll use g of x this time. We haven't used g today. There's my function. And I want to know, where does that function equal 0? And it's only going to have one solution. Okay, that's what my graph tells me. If I drew an accurate graph, which it's fairly accurate, they're only going to intersect once. Now the question is, where did they intersect? Because finding a starting point in this case might not be that easy. So let's first do our setup. Okay, so g prime of x would be 1 plus sine x. So x minus function over derivative. Now, in this case here, I don't know how efficient it's going to be to make this one quotient, but I still believe that one quotient may be easier to work with than this. So if I multiply top and bottom by 1 plus sine, I will get x plus x sine x minus x and I think the x's will cancel, and I'm going to get x sine x plus cos x on top, 1 plus sine x on the bottom. So therefore, my n plus first iteration equals xn sine xn plus cosine xn over 1 plus sine xn. So we want to solve this. And again, let's say I just need an answer. I don't need 10 decimal places. So let's solve to 2 decimals again. By the way, the more decimals, often the more steps it takes, but it doesn't mean for every decimal place, I have to do a bunch more steps. If I said, let's do 4 decimals, that might only take me 1 more calculation because they tend to converge really, really fast if I'm doing the problem correctly. What we don't know yet is what is our starting point. Now, remember, the starting point has to be a rational number. Ooh, so let's use some common sense here. That's pi over 2. This value clearly is between 0 and pi over 2. Pi over 2 is a little more than 1.5. Anybody have what do you think that good starting point would be?
Pi over 4.
Well, considering I have to be rational, pi over 4 is not rational, so that really won't help me much. Think rational. I'm between
1.
0 and pi over 2.
1.
How about 1? Yeah, 0 is a little too far. How about just use 1? Oh, okay. Yeah. Does that make sense? Why? Yeah, 1 would be a really good starting point. This isn't a polynomial. I'm not crossing an axis right now. Okay. I'm not drawing the graph of this. By the way, I don't want to draw the graph of this. This would be scary. Right? This would be a very, by the way, using the calculus techniques you've learned in the last few weeks, this would still be a very difficult graph to draw because you wouldn't be able to take a derivative and set it equal to 0 easily enough. Yeah, you actually would have to use Newton's method just to draw the graph. So I think the value of 1 would be a good starting point. If you said, how about 0.5? That would be a good starting point. The problem with pi over 4, although you said, well, it's exactly halfway between, well, but I'm intersecting somewhere in there. Pi over 4 is not a rational number, and my starting point needs to be rational so that I can input. Now, most important part of this problem, your calculator. Right now, what mode is your calculator in? I don't know, but what mode does it need to be in? Anybody want to guess?
Radians?
Radians. If I'm not in radian modes, my answer won't be very meaningful because I'd be doing the wrong calculations. Your answer has to be in radian mode. I mean, pi over 2, that's not pi over 2 degrees. So make sure your calculator's in radian mode. That will be critical. The only time this is relevant is if you're doing trig stuff, right? It doesn't matter the rest of the time because you're not doing anything triggish. So now I'm going to insert a 1, which is kind of easy on the first round because it's 1. So I've got sine 1 and cos 1. 1 plus sine 1. And I got, when I did that, I got the 2 decimals, I got 0.75. Okay. Now let's take 0.75 exactly. See, the thing about Newton's method, you're only using rational numbers. When you round off a decimal, that is a rational number. Now, the numbers that contributed to that weren't rational, but that is rational because that's 3/4. And now I'm inputting that until I get the same decimal twice in a row. So when I put 0.75 in now, I got on the phone. I think I just hit a wrong button. I hit a point. Oops. My key is stuck. Let me try that again. I didn't like that answer. There we go. Oh, my keys keep sticking. That drives me nuts. There we go. I got 0.74. Now do it a third time. Okay. What do you know? I got 0.74. So do I need to do it another time? No, I'm done. So what are we saying? we're saying these intersect at approximately 0.74. Now, how can I be certain? Easy. Let's take the cosine of 0.74. The cosine of 0.74 is approximately 0.738. So to 2 decimals, the cosine of 0.74 is 0.74. So that point would be the ordered pair, 0.74, comma 0.74. Beautiful. Now, this is the hardest type of problem to use Newton's method on, because first of all, there was no polynomial. There's not even a graph that's useful. You said, well, that graph's useful. That graph was 2 different functions simultaneously. That's not what you want. If I said draw the graph of this, this would actually be very, very difficult to draw, because again, I have a trig function with an x, and when you're doing derivatives, and yeah, it gets kind of dicey at that point. Now, let me tell you a real quick story. My daughter, who some of you may have heard me talk about, the chemist, she was a Mesa College student, and she got her associates in math and chemistry at Mesa College, then went on to University of Portland, got lots of scholarship money because she was in the Mesa honors program. That helped a lot, but she had no lab experience, career Starbucks kind of person. She had no lab experience. She's going into her last semester and she's never worked in a lab. Taking a lab class is not the same thing as actually working in a lab and doing research. And that is really necessary if you want to go on grad school, whatever. So one of her classes, it's like differential chemistry. I mean, really gnarly differential equations class in a chemistry class. And on the first day of class, the instructor asks them this question. It was gnarly. Really gnarly question. And he said, and here is a solution to this. And he gave them like a 2 decimal answer, a 3 decimal answer. And it was this really hideous equation involving something called Planck's law. Now, for those in chemistry, you understand Planck is very famous. I don't know much about Planck. I had to look him up. So she asked me, she says, I don't even know how to attempt this problem. And he asked the class, see if you can do this. So I said, it's a Newton's method problem. So I reviewed Newton's method with her. She does the whole problem using Newton's method, gives an answer that has way more decimal accuracy than the one he reported, and then explained kind of what was going on. The instructor actually says in front of the class, he says, oh, I didn't actually think anybody was going to try the problem. He said, I don't even know how to get the answer. He goes, I looked it up online. He was so impressed with my daughter being able to find that answer that he asked him, and his colleague asked her to assist them in their labs, in their research that semester. At the end of this semester, there's the only chemical research place in all of Oregon, practically, a company called Siltronic. They have a paid internship every summer that they offer to one chemistry student in the greater Portland area. There's a lot of colleges in that area. So my daughter applied, but had the recommendation of both of these professors. She got the internship, and it was a really good paid internship. And there's 4 major departments. They had her working in each of the departments over the course of the summer. Now, she graduated. This is post-graduation. She's graduated now, doesn't know what she wants to do in the fall yet. And she's like, I'm not ready to go to grad school yet. I don't know what I'm going to do. So she's working. The internship's coming to an end. But one of the people that she worked with decided it was time to leave. And so he left. So they kept her internship going for a few extra weeks. Then they advertised the position that the guy left for. They had 80 applicants, 68 PhDs, 11 with masters in chemistry, and my daughter with the freshly printed bachelor's degree in chemistry. But my daughter had worked there all summer in all 4 departments and had wowed them to the point where they hired her. Within a year, she's been promoted. Her title is chemical engineer. She runs an entire department. She's been on salary since, and she's in her 3rd year of grad school that they're paying for part-time. So why am I telling you all this? Because she solved a problem using Newton's method on the first day of class of her 2nd semester of her senior year, that had she not done it, this whole avalanche of things happened. None of them would have happened. She never would have got any of the lab and research internships, all these kind of stuff. But because, now I'm not saying Newton's method is the key to your future, although it might be. But the fact is, she went out on a limb, did something nobody else did. No other student, by the way, had tried this problem. And the instructor told her, he goes, I ask this every semester, nobody ever tries it. but because it was something relevant. When I've taken graduate stats courses, almost all the formulas are derived using Newton's method. So Newton's method is a really powerful tool. I just want you to be aware of it, and it's kind of cool. Now, we're going to completely change gears because we're done with the derivative half of calculus. So now we're going to go on in a completely different direction. And you're going to like this because it's not going to feel entirely new to you. Now, I want you to think baby algebra. In remedial algebra, you learn how to multiply polynomials. So I give you a binomial times a binomial, and you multiply it out. Maybe I give you a trinomial times a binomial, you multiply it out, you add like terms, you simplify. It's pretty automatic. There's not a whole lot that can go wrong. Then later in the algebra course, you're given this simplified polynomial and you're asked, where did it come from? What things got multiplied to give you that answer? Ooh, that's a harder problem. Now you have to factor it. So multiplying polynomials is one direction. Factoring is reversing the process, but it's a harder concept. So imagine now, we do a calculus analogy of this. I'm thinking of a function and the derivative of the function is 2x. Can you tell me what the function is? I'm asking you to work backwards. X squared is a great starting point. Do we all agree that x squared would be a good answer? But that's not the one I was thinking of. See, I was thinking of x squared plus 3. And I know Jeremy was thinking of x squared minus 5, and William x squared plus pi, just to be ornery. And Nate, of course, was thinking x squared minus 7. And are we all right, by the way? Every one of us?
Yes.
Yes. That makes it interesting, doesn't it? So what we do is we say x squared plus c, where c is what is called an arbitrary constant. C could be literally any real number. The x squared we're all pretty certain of. Now, why is there a constant there? Because when I take the derivative of this, I will most definitely get this. So I'm going to show you something. I'll give you a kind of a higher end thought process. Okay, x squared, perfectly good answer. But what about x squared plus 1? What about x squared plus 2? What about x squared plus 3? What about x squared minus 1? What about minus 2? I could do this all day. I often do. This is what I affectionately refer to as the Candelabra of Parabolas. Try saying that fast. All of these are answers. There's an infinite number of answers. All of them are answers. What if I only want one of them? Then I would need to give you more information. So what if I said f prime of x is 2x and f of 1 is 4? What if I said both things? Oh, this is called an initial condition. Exactly how many of these parabolas pass through the point 1, 4? Exactly how many? Anybody?
1.
Only one of them can. If f of 1 equals 1 squared plus c, and that equals 4, that must mean my c is 3. Ah, that would be this one right here. This one is the answer. So the answer to this question is f of x is x squared plus 3. So generally speaking, when you're working backwards, you throw an arbitrary constant at the end because you can't know what the constant is, because all constants are fair game. But if you're given an initial condition, then you can always find the value of the constant. Okay, so this is an extra thing. Now, what I just did was I worked backwards. This is called the antiderivative. That just sounds so negative, I know. You differentiate in one direction, and your answer is the derivative. You do what's called integrate in the other direction, and your answer is called the antiderivative. Okay. Now, my youngest son is taking calculus right now in high school, and he was confused on, well, what's the difference between integral, integrate, antiderivative? What is? I'm going to explain that because some of them are nouns and some of them are verbs, and that's why you can't use certain words interchangeably, right? So we want to make sure we got that. So the way we write it, and the notation is actually quite important. When you first learn derivative notation, most people just, they screamed and stomped their feet and said, this is horrible. And then once you get the hang of it, you go, okay, d dx is an operator that tells me differentiate what's following. Now I'm going to introduce what's called an integral. An integral is a symbol, looks like that. Some people like to call it an elongated S. If you want to call it that, that's fine. It's not an S. It's long and it's kind of curvy. The symbol means you're going to find the antiderivative of what's in there. So I'm going to put a little blank. There's something in there. And then I'm going to put a dx. I'm going to assume we're working with x at the moment. This is the instruction. These two things go together. This says find the antiderivative of whatever's sitting here with respect to the variable x. So what's sitting here might be, let's call it f prime of x. And when I do that, my answer will be f of x plus some arbitrary constant. This is not a quantity. Now, similarly, when you did this, this instruction was, I have some function f of x. I'm going to take the derivative with respect to x, because remember, I could do it with respect to another variable, and then we just use chain rule. I'm going to apply this operator to this, and my answer was f prime of x. Oh, same dx. So now in reverse, I'm going to integrate f prime of x with respect to x and get back my original function. So this is the loop here. The integral is sort of the inverse of the derivative, sort of. The plus c means I can get multiple answers, but I'm still going to get the same f of x back every time. Okay, so that's how we write it. Now, we already know about at least 20 derivative formulas. So what's beautiful is if we know a derivative formula, then we can actually go backwards relatively simply. For example, if I know that the derivative of the sine of x is the cosine of x, then that means the antiderivative of the cosine x dx must be the sine of x. And then we throw in the plus c. Right? These go hand in hand. Every derivative formula that you know, if you write it left to right, it's the derivative. If you now think of it right to left, it's the antiderivative. Kind of like multiplying polynomials out and then factoring them in the reverse. It's actually a very similar process, which is why most people take the integration rather quickly. But integration is harder than differentiation because sometimes you have to manipulate. Sometimes you got to do a little work before you can find the antiderivative. Now, let's go with one we know well. Probably the most common type of derivative we know is if I differentiate anything of the form x to the n, we know the answer is n x to the n minus 1. That's not even a question. We know this. So here's my question to you. What if I want to do this? I want to integrate this. Integrate is the noun. My result is the antiderivative. Okay, so this statement is, this is the integral of x to the n. I want you to integrate x to the n. My answer is the antiderivative. Okay.
Doesn't that make integrate a verb?
Yes. This thing is an integral. I want you to integrate. That's the operation I want you to perform. And my result is the antiderivative. My result is not the integral. The integral is the statement of the problem that hasn't been done yet. After I do the problem, my result is an antiderivative. That's the kind of the nomenclature, because a lot of folks get confused. They're going, wait, what am I doing here? I see integral, integrate, antiderivative, antidifferentiation. Antidifferentiation is the same as integration. Integration, right, is the operation that you're doing. Okay, it's like saying I'm going to go running. So I want to do this. If differentiating means I reduce the exponent by 1, do you suppose that integrating means that I should increase the exponent by 1? Does that seem reasonable? What do you think? Does that seem reasonable as a starting point? Everybody, please.
Yes.
Yeah, it seems reasonable as a starting point. Now, what I don't know is, I know there's gonna be a plus C. What I don't know is if there's gonna be a coefficient. So I'm gonna put A. I don't know what A is, but I'm gonna put A and figure it out. But this seems absolutely reasonable. This seems absolutely reasonable from the standpoint of, I know when I differentiate, I lose one. Now, one thing that must be true is, tell me about n. Well, we'll figure, are there restrictions on n? Actually, there is, but we'll go over that in a moment. Now, how do I figure out what A is? Easy. Let's differentiate. The plus C is not that important because it's going away. Let's take the derivative of this. All right, that would be A times n plus 1 times x to the nth power. So does everybody agree with that? If I differentiate this, I get this. Now, what's this supposed to be? It's supposed to be this. This guy here, the function in your integral is called, it's funny, we run out of cool words. This is called the integrand. X to the n, the thing that I'm integrating is called the integrand. So the integrand would be the noun. I'm going to integrate the integrand. I know that sounds like circular reasoning. No. Everything has a name. Okay. Now, I'm supposed to get that back again when all is said and done. Well, that would mean that this quantity here has to equal 1. And the only way that can occur is if A equals 1 over n plus 1. Oh, okay, I think we got something here. That means the antiderivative of this is 1 over n plus 1, x to the n plus 1. We just figured it out. I didn't tell you we figured it out. Now, when I take the derivative of this, what happens? N plus 1 comes down, cancels that guy. Beautiful. Beautiful. So that all works. Now, limits. Limits are cool things because I can do the limit of anything and get anything. But there were two very important limit properties that translated elsewhere. The limit of a sum is the sum of the limits. The limit of a scalar multiple is the scalar multiple of the limits. We know this. Those are the only two that translated to derivatives. The derivative of a sum is the sum of the derivatives, and the derivative of a scalar multiple is a scalar multiple of the derivative. Meaning I can factor the scalar out. Remember, the derivative of a product is not the product of derivatives and so on. Do those properties hold for integrals? Turns out they do. Let me show you. Okay, we know the following, that the derivative of f of x plus g of x equals f prime of x plus g prime of x. We know this. We proved this really early on. We had to use limits, actually. The derivative of a sum is the sum of the derivatives. So now here's the question. What if I want to do the integral? What if I want to do the integral of the sum? What are we hoping it is? Anybody, what are we hoping the answer to this is?
F of x plus g of x.
Yeah, we're because that would mean that the same property holds. Well, here's what we absolutely do know. If the derivative of this is this, then the antiderivative of this has to be this. So that's not really a question yet. But here's what I really want to know. Can I break this up? So as a separate tool here, what if I just do this and I just do this? The antiderivative of f prime of x is f of x. I don't have to prove that because the derivative of f of x is f prime. I'm just being really generic right there. And plus arbitrary constant. And this guy plus arbitrary constant. Now here's where we got to be a little careful. And this is sort of a simple rule to follow. When you're doing more than one integration in a problem, you don't want to put the same symbol here, because although c can be any real numbers, what did I just say about these two c's? I wrote plus C and I wrote the same plus C. What am I saying right now?
That they're the same?
They're the same. And actually, that's not even possible mathematically. Of the infinitely many real numbers that could go there, they have to be the same. No, they're not the same. Oh, so how do I C1, C2? That's what most people do. By the way, you can call it A and B. Just don't call them the same thing, because within the same problem, this is the same problem. Now, you'll see a bunch of formulas, and it'll have all the antiderivatives as being plus C, but each of these is thought of as a completely separate problem. So we're not saying they're the same C. We're just saying, hey, there's an arbitrary constant here. There's an arbitrary constant here. I'm saying within this problem, I'm doing both of these integrals. So let me call these different things. Now, look at this answer. Isn't this f of x plus c1 plus f of x plus c2? Because that's just f of x plus, I'm sorry, not f of x, sorry, g of x. If I took this answer and I added it to this answer, I have f plus g plus c1 plus c2. If c1 and c2 represent any possible real numbers, then their sum is still any possible real numbers. So we generally rename it as what we call it C3 or just C. So what have we just proved? That the integral of the sum is actually equal. This is equal to the sum of the integrals. We already knew that was the answer, but the question is really not what's the result, is that if when you differentiated a sum and we use limits, that was a really gnarly expansion. But once we learned that the derivative of a sum is the sum of the derivatives, then when you differentiated one term at a time. So now if I'm going to integrate a sum, what does it mean? I'm going to actually do the integrals one term at a time. And that will make my life so much easier. Now, what about the scalar multiple aspect? Well, we also know this. So the question is, if I integrate k f prime of x dx, I know I'm going to get k f of x plus c because that's where it came from. But if I factor out the k, then what will I get? I'm going to get k times f of x. Now, this integrand and this integrand are not exactly the same. This one's k times bigger than this. Therefore, their antiderivatives cannot possibly be exactly the same. Oh, so I'm going to call it a different constant then. I know the antiderivative of f prime is f. I know the antiderivative of this is this because that's where it came from. But if I called it the same c, that would only be true if these functions themselves were identical, and they're not. So I'll write it like this. Well, that's k f of x plus k c1, which I will just rename as c. Yeah, it's kind of clever, I know, but it works. The derivative of a sum is the sum of the derivatives. The integral of a sum is the sum of the integrals. The derivative of a scalar multiple is a scalar multiple of the derivative. Same thing with integrals. That means that you can do things one at a time. You don't have to look at something as a large thing. So let's do that with polynomials because those are our favorite things for now. I'm going to walk you through the process because it is not complicated. It is not difficult. And within a week, most of you are going to be really good at this, I promise. So I want to do the integral of how about 4x to the 6th. Okay. Now, if I asked you to do the derivative, you're not looking at the 4, you're looking at the 6, I would hope. Okay. So when you're doing the antiderivative, it's the same thing. Start with the exponent. So what's my exponent going to be in the answer? Anybody? It's going to be a 7. Therefore, the coefficient does not involve 6. It's going to involve 7. There's going to be a 1/7. But what do I do with the 4? Multiply times 1/7. That's it. There's no in-between step. I increased by 1, and then that showed up in the denominator. What about the 4? It's still there. Now, quick check. Always check right now. If I differentiate, I bring down the 7, and 7 times 4 sevenths is in fact 4. Yep, I'm going to get it back again. This process should be very fast. There's nothing about this process that should ever trouble you. Not this. Okay, so when will it get tricky? Well, if I had asked you to differentiate this, would any of you have differentiated in this form? Probably not.
I changed that X for.
Yeah, you'd write it as an exponent, because when it's on the bottom, I can go backwards, right? I can go the wrong direction inadvertently. So I think if I said differentiate this, I think all of you would have written it as 6 times x to the negative 4. Am I correct? Yeah, so therefore, if I'm integrating it, I actually want to do the same thing. Because now, when I add 1 to my exponent, my new exponent is going to be negative 3. So my coefficient is going to be negative 1/3 times 6. That's it. Now, quick check. Positive 6, x to the negative 4th. Beautiful. Now, I'm done with the calculus. Would we consider that a good finished answer?
Send it downstairs.
Yeah, I got a negative exponent. I should write that as negative 2 over. By the way, don't move the 2. So the antiderivative of this in its best form would be this. The process is not hard. It's bookkeeping. You just got to make sure on top of things. So there's one other one that sometimes gives us trouble. Oh yeah, the root. Now remember, you can't differentiate a root for the same reason you can't differentiate this guy, because I need it in an exponent form. Well, the rules for differentiation and the rules for integration when it comes to x to a power are really, really similar. Same sorts of restrictions. So in this case here, first thing I would do is rewrite this as x to the 1/2 power. Now my answer is going to be x to the what?
3 over 2.
3 over 2. Now, what goes in front?
2 over 3.
2 over 3. The reciprocal of that guy. And I'm done. Can I leave it in this form? Is this considered finished?
Absolutely.
Yes. In fact, I think it would be unwise to rewrite that as a root. I don't think it's as useful. Square root, cube root, 4th root, that's okay. But when you have fractional exponents, 3/5, 4/7, whatever, I think writing it as root to a power, it can get a little bit confusing. Plus, remember, you cannot do the derivative or the integral until you change it back to the fractional exponent anyway. I would just leave that. I don't see any advantage to rewriting that. It would not be incorrect, but I don't know that it's an improvement. So there's my answer. And my check is simple. I bring the 3/2 down. Okay, life is good. So that process is not really complicated. So let's do something a little bit bigger. Okay, I'm gonna tax you now. I want to do the integral of 4x to the 7th minus the secant squared x plus e to the x dx. Now, when I'm doing this, you do not need to rewrite it as integral plus integral plus integral. That's overkill. When you're doing the problem, do it one integral at a time. But the next thing I write should be my final answer. There is no in between. So I'm going to integrate this guy, and then I'm going to add it to the integral of this guy, and then I'm going to add it to the integral of this guy. Now, do I know those antiderivatives? Yes, actually, I do. I do know those antiderivatives. I'm going to walk you through, because the easiest way to think of an antiderivative is to say, what function did I differentiate to get here? That's actually the way you think about it. Believe it or not, that's how all of you learned to divide when you were in elementary school. That's how all of you learned to subtract. You may not realize that. This is actually the technique that was taught for a couple hundred years. I'll give you an example. If I said 8 plus blank equals 10. This is called the missing addend approach. This is how all of you learn to subtract on day one. You may not realize that. You see, what's the answer? It's 2. How do I actually get 2? Isn't it 10 minus 8? And when I say 4 times blank equals 8, what do I multiply by 4 to get 8? 2. Well, where does the 2 come from? That's 8 divided by 4. That's called the missing multiplicand. That's a horrible word. This is how everybody basically on planet Earth, for the most part, learned to subtract and to divide, is you started with a sum and a product with a piece missing, and it forced you to work backwards. This is actually how we integrate. We do the exact same thing. What function, when I take its derivative, will look like this? That's actually how I want you to think. So clearly it's going to be an x to the 8th. What would the coefficient be?
1.5.
And where did that come from?
Just putting
4 over 8.
Yeah, 4 times 1/8, 4 over 8, exactly. I don't care so much as the right answer as that you know where it came from. Otherwise, you might not be able to reproduce it. Now, can you think of any functions whose derivatives look like secant squared?
tangent.
Tangent. So minus tan x. Can you think of any functions whose derivatives look like e to the x?
E to the x.
E to the x, okay. And by the way, this is something that's very important. You did the first integration plus c, the second integration plus c, the third integration plus c. No. You only have one problem. There can only be 1 plus c, and you wait till you're all done to put it. There's a tendency, I will see people put this plus c, this plus c, this plus c, and first of all, they use the same plus c 3 times. Wouldn't that add up to 3c? No, don't do that. Okay, then plus c1 plus c2 plus c3, then I'll add them together. No. When you're doing an integration problem, there's only one plus constant, and you simply have to wait till the end of the problem. Because if I differentiated this, I'd go derivative, 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 and that's 0. And I get this back again. So the plus c at the end, that should not be taxing in any way to you. Okay, so far so good? You say, I can do this. You know a lot of formulas. Now, what do we consider the most important formula for derivatives in general? The most important part of when you're taking a derivative, what is like the most important, biggest thing that applies across the board to all derivatives? You remember?
The product, the chain rule.
The chain rule.
Yeah.
Because it applies to every derivative you ever take. The most important part of integration is the chain rule. That we start next day. And I did that on purpose because of all of the things you learn in Calc 1, it is number 1. It is number 1 of the single most important thing you learn in Calc 1 is the chain rule for antiderivatives. The most important thing you've learned up till now is the chain rule for derivatives, but now we have to have a version for antiderivatives. That's next day. We're not doing anything that requires a chain rule today. No, not even close. We have to get this down before we can start getting complicated. We learned how to take the derivatives of all of our functions, sine x, cos x, e to the x, before we started worrying about compositions and chain rules. So the same thing, we're going to go through how to integrate each of the simple versions, and then we will do chain rule starting next day. So that's not on this exam, and that's by design. That gives you a longer time to master that. So now we're going to do a very simple application, but one that's considered very, very important. We're going to solve what's called a differential equation. Wait a minute, we just started integration. We're doing differential equations. That's math 255. No, a differential equation, we've already solved one. The very first thing I wrote, when I said this, and you all told me this, which you all did basically, you just solved a differential equation. This is a differential equation. This is the solution. The term differential equation just simply means an equation involving a derivative. That's all that means. In Math 255, which is after calculus, you just solve gnarlier ones. You're going to solve a bunch of differential equations in the first couple of weeks of Calc 2. You do differential equations all the way through calculus on occasion. You don't do complicated stuff. You're just introduced to different versions. So we want to do a differential equation right now. I'll walk you through it. I'm going to tell you the following. F double prime of x is 3 cos x minus 2 sine x plus let's say 12x. Okay. F of 0 is 4. F prime of 0 is -7. I want you to find f of x. So in Math 255, we would call this a second order differential equation with constant coefficients. It sounds scary. No, it's pretty easy. I need you to find f of x. I've given you the second derivative. So what do you suppose the first thing you have to do is? Anybody want to try?
Find the first derivative.
And the first derivative. And how would I find the first derivative? I integrate. So f prime of x is going to be the antiderivative of all of that stuff. Okay. Rather than memorize rules. And by the way, everybody in Calc 1 is pretty much an expert on sine and cosine at some point. Everybody's an expert. But any errors that you've ever made on sine and cosine, it's always the same error, isn't it? Plus or minus signs. Do you all agree with that one? If it's sine and cosine, I got to do derivatives, it's the plus and minus. I sometimes get them backwards. Derivative of sine is positive cosine, derivative of cosine is negative sine. Now I'm integrating, I have the same problem. It's still the plus or minuses that give me issues. So if you try to memorize a whole bunch of formulas, you're going to get in trouble. It's much easier if I said, what function when I differentiate it gets me to cosine? What function when you differentiate gives you cosine?
Sine.
Sine, positive sine, agreed? So this is just 3 sine. And quick check, the derivative of 3 sine is 3. Okay, good. What function when I differentiate it gives me sine? Well, I'd have to differentiate a negative cosine to get sine. So I have to differentiate a positive cosine to get me to a negative sine, don't I? What about the 2? Just goes along. Quick check, derivative of positive cosine is negative sine. Okay, good. So far, so good. What do I have to differentiate to get a 12x? Well, it's going to have an x squared, and my coefficient is going to be
12 over 2,
12 over 2,
which is 6.
Everybody cool so far? So that wasn't that hard. Plus C1. Now, why am I going to call it C1? Because I got to integrate twice. And I'm going to use those initial conditions to help me figure out what the C is. Now, we're almost halfway done. We're not halfway done yet because I haven't figured out what C1 is. So f prime of 0. So let's plug a 0 in all the way across. 0. 2. 0 plus C1. Okay, do you all agree with that? If I evaluate this at 0, I'm going to get 2 plus C1. And what is f prime of 0 equal to? -7. So what does that mean? That means that C1 is -9. Now I'm halfway done. Now I can say that f prime of x is 3 sine x plus 2 cos x plus 6x squared minus 9. And that minus 9 is actually quite important. It's not going away. So now f of x, I'm going to take the antiderivative of this. Hopefully I left myself enough room. I wrote kind of big. 3 sine x plus 2 cos x plus 6x squared minus 9 dx. All right, using the same reasoning we did a moment ago, what do I have to differentiate to get me to 3 sine x? Anybody? Well, I'll go out on a limb. I'm pretty sure it involves a cosine. In fact, I'm pretty sure it involves a 3. But is it positive or negative?
Negative.
The derivative of sine is positive cosine. The derivative of cosine is negative sine. So I need a negative there. Okay. And rather than memorize formulas, work backwards. What do you have to differentiate to get you to cosine again? Positive or negative sine?
Positive sign.
Positive sine. Okay. Derivative of sine is cosine. Remember, the derivative of this will get me back to here. Okay. Well, I don't have to think. That's going to be an x cubed. Okay. And what's my coefficient going to be?
2.
2. That's it, right? Oh, wait a minute. Oh, is it zero? The derivative of what gives me a constant?
9x.
9x.
Sorry, x.
9x. The derivative of negative 9x is negative 9. Oh, so think of this. Constants are polynomials of degree 0. So I have to have a degree 1 here. See, differentiated x cubed to get x squared, you differentiated x to get constant. That's consistent with what you already know. Funny thing is, the easiest derivative to take is one of a constant. But everybody at first is troubled when they're integrating a constant because they want to put a 0 down. No, it just, you get a linear function then, plus C2. All right, so just like before, what is f of 0? -3, 0, 0, 0, plus C2. And that's supposed to equal 4, which would imply that C2 is 7. Okay, with that, I can now give you the final answer to the problem. I'll put it, actually, you know, I'm going to erase these. I don't need these anymore. I'll put it right here. So my answer is f of x equals, so I'm not done until I state the final answer here, -3 cos x plus 2 sine x plus 2x cubed. Where are we here? Plus 2x cubed, oh, minus 9x plus 7. I'm pretty sure I did this right. Pretty sure. Can we have certainty?
Then you take the derivative of it to double check.
Work backwards. If I take the first derivative of this and evaluate it at 0, okay, part of it is so that I get the right constants. Now I'm going to take, by the way, if I just said take 2 derivatives of this, I think everybody's going to get this back again. I have no doubt that you're all going to get that back again. But the problem is I also need those terms to be right. And that's where I would check it by evaluating it at 0. So right now, the first thing I'm going to do is evaluate this at 0. I'm going to have -3, 0, 0, 0 plus 7. That's 4. F of 0 is 4. That was given. Yes. Take the derivative. I'm going to get this, evaluate this at 0. It also worked. I take the derivative one more time. I get the original. Life is good. We just solved the second order differential equation. That's probably the most work you're going to do in any problem really this semester because of how many steps. None of the steps were hard, but every step was necessary. There isn't a step here I could have skipped. If I could have, I'd show you. If a step can be skipped, I will show you that because it means you're not really needing it. When we first started doing product rules and chain rules and different things, and we wrote down every detail of every step, and then eventually we'd say, well, you know, we can just go ahead and start differentiating without rewriting. And we found ways of being efficient. But in terms of integrating, you really can't skip steps. You have to integrate each thing. If you were only given the first derivative and asked for the function, that's easy, one integral. Normally, you're just simply given an integral and you're told to evaluate. So that means perform the integration, okay? If I gave you a function, I put d dx in front, I'd say evaluate. That means, oh, perform the differentiation because you understand what the terminology is. So that's about where I wanted to get today. Now, our next exam looks like, hold on, where are we? The end of next week. And it goes through obviously what we just did today. I've gotten a few questions over the break. People are asking me, you know, I want to prepare ahead of time. What sort of things? Well, this exam covers lectures. I'm sorry, where are we? Covers lectures 9 through 16. The first 8 lectures were the first exam. The next 8 lectures are this exam, which means that's the material you're being tested on. So you're saying, I don't have to know anything from the first 8 lectures. Well, actually you do. I'm not going to ask you questions from the first 8 lectures, but we learned more derivative formulas in the second one. But if I ask you a derivative formula involving, let's say, a logarithm, what did we do? Like an inverse trig function, for example. Or a hyperbolic function. I could be asking you an inverse trig function of a polynomial, but polynomials came from the first test. Yeah, but now I'm doing an inverse trig of a polynomial. I still have to know how to differentiate a polynomial. I still have to know how to do product rule, quotient rule, and chain rule, because those still apply to the derivatives I've learned this time around. But obviously, if you're looking at the schedule, a great bulk of this exam will be applications and graphing concepts and things like that. So those are the main things. And all of those involve, of course, derivatives. So 7 of the 8 lectures you're being tested on are related to derivatives. Today, we have some integration. So the integrations you're going to do on the exam are going to be pretty low level. So those who looked at the practice test, it probably scared the heck out of you because you saw integrals and go, what are these things? Now you go, oh, that's all they are. So the integral of a polynomial or the integral of a sine or a cosine, those are going to be very low level. Those are things that actually most of you will find fairly simple. The later integrations are going to get more complicated, but that's next day. All right. So this is a good stopping point. We covered a lot of ground today.